All right, welcome back to my numerical analysis class. In this video, I'm going to be talking about Lagrange interpolating polynomials. Okay. All right, in my previous lecture, I already motivated this interpolation called Lagrange. And we've shown that if I have n plus 1, if I have n plus 1 grid points, and here we denote it as delta, so as 0 up the way to xn, that will be n plus 1 grid point, okay? And I have the collection corresponding coordinates y0 all the way to yn. All right. We've shown in the previous theorem that there exists a unique polynomial f star of degree less or equal to n that interpolates yi at xi for each I 0 to the way to n. All right, so we started to talk about a particular one, which is Lagrange interpolation. Actually, we derived that in the previous lecture. And basically, is the interpolation that is given by this formula, I from 0 to n, yi li of x, where li of x is a basis function. Okay. Li of x is a product, okay, from j equal to 0 to n. J is different from I, x minus xi over xi minus xj. Sorry, this is j. And I moves from 0 to n. All right, this is Lagrange interpolating polynomial. Show that this is unique. It exists and it's unique. Okay. And the topic in this video will be to provide and to prove the error for this approximation and solve some further examples. So let's quickly go into the error statement. All right, so Lagrange error formula states this. If I have x naught up to xn, they are distinct in the interval AB, and I have a function which is cn plus 1 on this interval. Then for each x in this interval, a number theta, generally unknown, between x0 to xn, between AB, there it exists with this error terms formula given. Okay. The function f is the function we are approximating. The f hat is the Lagrange interpolating polynomial. So the goal here is to prove this error formula. So let's start with the proof. All right. Proof. Okay. I want to break this in cases, okay? Case one, if the function we are approximating is already a polynomial function of degree less or equal to n, we are done because I just showed you before, I just talked about the uniqueness of polynomial approximation. So by uniqueness, of the interpolating polynomial, we must have that the function the approximation we are looking for is exactly the same function, since already a polynomial. The error is 0 because of this term. And the proof is done. All right, so case 2, let's assume that f is not a polynomial yet of degree less or equal to n. All right, so under this case, I'm going to take a subcase, call it subcase A. If x is xi for some I, what we get here is that EXI is FSI minus F hat SI. Remember that FXI is exactly F at XI. We are finding the interpolating polynomial means that the polynomial approximation that we have should be the same on every other grid points. So this is 0. And the result is true. Now, let's go to subcase B, where x is not the same as xi for every I. So subcase B, x is different from xi for each I. Okay? Let's keep that. Now I'm going to define series of some functions that will help me to prove what I need to prove. So first, I'm going to define this function. Phi of x is the product from I equal to 0 to n of x minus xi. Now, before I go ahead with what I need to do, I want to state some properties of this phi. The first thing you should notice from this is that this is a polynomial of degree n plus 1. Okay, it starts from 0 and it goes all the way to n. So that's a polynomial of n plus 1, 2. Phi of xi is 0. That is one of the terms in the product is 0. Okay. X minus xi minus xi will be 0. 3, if I differentiate this function n plus 1 time. All right, so if you have a polynomial of degree less or equal to n plus 1, okay, polynomial of degree less or equal to n plus 1. If you differentiate it first, you get n plus 1. If you differentiate it next, you get n. If you differentiate it next, you get, so if you differentiate 5 first, you get n. 5 to the prime of x is n. Okay, I'm talking of the coefficient now of some function. If you differentiate it next, you get, sorry, the first one would be n plus 1. The next one will be n plus 1 n of some function. If you continue this way and you go to n plus 1 of x, you realize that what you get next will be n plus 1 and n minus 1, and that until you get to n plus 1 and n minus 1, n minus 2, until you are at the last one, which is 1. And at that point, the function is constant, so you cannot proceed. So what is going to, if you combine all this, you have n plus 1 factorial. So the derivative of 5 to up to n plus 1 is going to be n plus 1 factorial. So these are very important properties of phi, which I want us to keep in mind as I proceed with the proof. All right, before we continue again, I want to define some functions. So I want to fix t in a way that is between the interval and I don't want t to be xi for any I. So t should be something else other than this point. Now that I have the t, let's define these functions. First, I want to define k to be f of t minus f hat of t over phi of t. I know what is f. F is the function I'm approximating. F hat is the approximating function, polynomial, and then phi hat is what we defined before. And so once I have this k, I'm going to define a new function g of x to be f of x minus f hat of x minus k phi of x. All right, first, let's look at this function g. F is, by the statement of the theorem, f is in Cn plus 1 of AB, okay? F hat is a polynomial by design, so is C infinity of AB. So automatically, this is a combination of two functions from Cn plus 1 and C infinity, because K is made up of functions from the same thing, phi is made up of function. It's a polynomial C infinity, so G, this implies that G will be at least Cn plus 1 AB. Okay. Now, the next thing I want to do is to study the zeros of G. What are the zeros of G? Okay, so G, zeros of G. Let's see. First, let's put in xi into G. If I put xi into G, I'm going to get f of xi minus f hat of xi minus k phi of xi. Remember that this guy is 0 because f is the same, f at xi is the same thing as f at as at xi. Phi of xi is 0 with one of the properties we showed before. So everything is 0. It is g of xi is 0. If g of xi is 0, this implies that, and this is true for I, 0, 1, up to n. This implies that this implies that xi is 0 for g. For each. All right. So how many zeros do we have here? We have n plus 1 zeros. But before I go into that, let's look at another one that could be possibly 0. Let's put in t. G of t, okay, is f of t minus f hat of t minus k phi of t. So let's evaluate this. So this is f of t minus f hat of t. Who was k? K is f of t minus f hat of t divided by phi of t times, now I have phi of t here. So clearly phi of t cancel out. So what I have is f of t minus f hat of t. If I distribute this negative, I have f of t, then plus f hat of t. So f of t cancel out, f hat of t cancel out, so I get 0. It means that g of t is also 0. So t is a 0 for g. So in total, in the first one, we have n plus 1 zeros. In the second one, we have 1 0. So g has n plus 2 zeros. Particularly, we are talking about the interval AB. T is also inside AB. What does this mean? Let's analyze it. So G has at least, and I should have put the word at least, not exactly, at least, okay? Which could be less. In this case, we saw all of them. So G has at least n plus 2 zeros on AB. If I differentiate G once, it will have at least n plus 1 zeros on AB. If I differentiate it less, it will have at least n plus 1, at least n zeros on AB. If I continue this way up to when I differentiate G n plus 1 times, it will have at least, since I started from when it is 1, I have n plus 1. Now when it is G plus n, I should have at least 1 0 on AB. What does this mean? It means that there is some number between AB such that G G, derivative of G to the n plus 1 of that is 0. So let's say zeta is that guy. What we are saying in essence is that G of n plus 1 of zeta is 0. Okay. Let's go back to G. So G initially was given to be this guy. And I want to differentiate G n times. So G n plus 1 times rather will be derivative of the first guy to the n plus 1 term minus the derivative of this one to the n plus 1 minus k to the derivative of this one n plus 1 term. Remember that f hat, okay, f hat is a polynomial of degree at most n. This means when I differentiate a polynomial of degree of at most n, I'm differentiating it n plus 1 times, it means that the derivative will be 0. The derivative is 0. So this term practically is 0. We have seen that in the property free of phi, this is n plus 1 factorial. So, and we've shown that this guy, so we have at the end of the day that Gn plus 1 of x is Fn plus 1 of x minus k n plus 1 factorial. So when x this means that at point x, this is for all x in AB, okay? So particularly for zeta, we will have Gn plus 1 of zeta equals to Fn plus 1 of zeta minus k n plus 1 factorial. K here is a constant because it's not. All right, so what we get here is that the left-hand side is 0. We saw that in the previous slide. This one is 0. Eventually, we have f to n plus 1 of zeta x minus k. We can just separate it to be this. Okay. Let's introduce what is k now. So Fn to f to the n plus 1 of zeta x is f of t minus f out of t divided by phi of t times n plus 1 factorial. Okay, now let's move things around. I have f of t minus f hat of t equals I will multiply this one with this and divide by this, guys. So if I do that, I'm going to get fn plus 1 theta x over n plus 1 factorial times phi of t. You know, we started with arbitrary t. We then have that holds for any t in AB, so just for any x in AB. So f of x, f hat of x equals fn plus 1 zeta x over n plus 1 phi of x. And we know it's phi of x. So this is fn plus 1 of zeta x over n plus 1. Phi of x is the product j equals to 0 of n, x minus xi. I should be different from j should be, no. If you want, just use I. That is the theorem that we approved. All right, so we now know the error for this approximation, okay? So then let's go into solving some examples. Okay, the first example here is given this function, we know this function very well, exponential x. And we have this point minus 1, minus 0.5, 0, 0.5, and x4. The first question is to find the Lagrange interpolating polynomial f hat of degree less or equal to 4 that passes through the point or this point. And B, find an upper bound for the difference at x equal to this and this between f of x and f hat of x at the points x0, x1, x2, x3, and x4, right? So let's solve this problem. Solution. It's a very lengthy one, so just bear with me. All right, first, realize that the capital N here is 4. All right, so if we go by the formula that we've done before, f hat of x, the approximation that we are finding here is the sum from I equals to 0 to n, but n is 4 here, so yi li of x. And if you want to write it explicitly, this is simply y0 L0 of x plus y1 L1 of x plus y2 L2 of x plus y3 L3 of x plus y4 L4 of x. Okay, so first let's find out the y's. We have the function and we have the point. So y0 will be e to the power x0, which is e to the power minus 1, which is 1 over e. y1 is e to the power x1, which is e to the power minus 0.5, which is 1 over e to the power 1 over 2. y2 is e to the power x2, which is e to the power 0, which is 1. y3 is e to the power x3, which is e to the power 0.5, which is e to the power 1 over 2. And lastly, y4 is e to the power x4, which is e to the power 1, which is e. So we can write the function back as 1 over e L1 of x plus 1 over square root of e L2 of x plus L3 of x, because y3 is 1. So y2 is 1. So I'm sorry, this should be 0. This should be 1. And this should be 2. Y2 is 1. So plus e to the power 1 over 2 L3 of x, then e L4 of x. So actually the main job here is to find the basis function, the Lagrange basis function here. So I'm going to show you how to find a couple of them, then I will trust that you can find the rest on your own. So let's start with L0 of x. Since we have 4 points, Lagrange, this function will be x. Now, I'm going to omit I equal to 0, so the rest will be involved in the product at the top. So it will be x. I will start from x1, since x0 is going to be excluded in the top. So I'll move all the way to all the points, x2, x3, and x4. All right, now the lower, the denominator here would now be x0. You start with x0 and make sure that what you have here corresponds to what you have done. So it's going to be x1, then the same x0 minus x2, the same x0 minus x3, the same x0 minus x4. Recall that x0 is missing because we are finding L of 0. L0, okay? And at the denominator, this thing is the same all through. The only thing that is changing is the only thing that is different is the first term, is the first part of the bracket here. And that is x0, the missing guy on the top. Okay. And so this is simply x1 will be x minus x1 is, so that will turn to plus half. X minus, that will turn to minus 0 or plus 0, that's fine. X minus 1 over 2 and x minus 1 over x0 here is minus 1. So you have minus 1 plus 1 over 2, minus 1 plus 0, minus 1 minus 1 over 2, minus 1 minus 1. Excuse me. If you use your calculator and do the arithmetic, you get x into x squared minus 1 over 4, since this is different of 2 squared, these two guys. And then I have x minus 1. Everything on the denominator will be 3 over 2. So finally, what you will get is 2x, x squared minus 1 over 4, x minus 1, everything over 3. I'm going to find L1 of x as well. So the same way, x1 will be missing. X1 will be missing at the top. So I'm going to have x minus x0. Instead of x minus x1, x1 will be missing. So it will be x minus x2, x minus x3, x minus x minus x4, all over the same method. So what's missing is what you are going to be using to subtract down. So x1, then x0 is here, so I'm going to have x0 here, x1, then I'm going to have x2 here, x1, I'm going to have x3 here, x1, I'm going to have x4 here. And if you make the substitution again, you will have x minus minus 1, which is x plus 1. Then x minus 0, remember that x1 is missing. Then you have x minus 1 over 2 and x minus 1 minus 1. So everything divided by, now I'm going to use x1 to make the subtraction. So I'm going to have minus 1 over 2. If you like, you use 0.5. I usually avoid decimals. So minus 1 over 2 plus 1 here, minus 1 over 2 plus minus 0 here, minus 1 over 2 minus 1 over 2 here, minus 1 over 2 minus 1 here. And if you, again, you see that this guy and this guy, they are different of 2 squares. So I'm going to have x, because x minus 0 is x. I'm going to write the difference of 2 squared, which is x squared minus 1, and then x minus 1 over 2. Everything is divided by minus 3 over 8. If you write it very nicely, you're going to get minus 8x, x squared minus 1, x minus 1 over 2, all divided by 3. Because of time, I'm not going to walk through everything. I'm going to give you what L2, L3, and L4 will look like, and that would be, and I trust that you can walk through, use the same way to get that out. So L2 of x, if you use the formula, you will end up getting 4 into x squared minus 1, then x squared minus 1 over 4. Or simply x squared minus 1 and 4x squared minus 1. And for L3 of x, you get minus 8x into x squared minus 1, x plus 1 over 2, all divided by 3. And L4, similarly, will be 2x into x plus 1, x squared minus 1 over 4, divided by 3. So finally, we can now write very long expression as our approximating polynomial, which, if you substitute all the L0 to L4, you will get 2x into x squared minus 1 over 4, x minus 1 over 3e, already put in the y naught, minus 8x, x squared minus 1, x minus 1 over 2, divided by 3e, plus x squared minus 1, 4x squared minus 1. This has no corresponding y. Y2 is 1. So minus 8 square root of e, x squared minus 1, x plus 1 over 2, all divided by 3. Now you get the last one will be plus 2e, x plus 1, x squared minus 1 over 4, all over 3. That would be the approximating polynomial. Now let's discuss the second part, the B part. So the B part says find an upper bound for the difference at this point. So first, let's use the Lagrange error formula that we proved at the beginning. So the Lagrange error formula will give us remember that n is 4 in this case, so E of x will be f of x minus f hat of x, which is f to the 5, n plus 1, which is 5, of some zeta over n plus 1 factorial, which is 5 factorial, times the product x minus x naught, x minus x1, x minus x2, x minus x3, x minus x4. And if you write that clearly, you will get what you have there will be f to the 5th zeta x over 5 factorial, which is 120. And you get x minus x plus 1, x plus half. If you put those points in, you have x minus 0, x minus half, and x minus 1. All right, so the interval we are working on is -1 to 1. So zeta here is in between -1 and 1. All right, so we want to find upper bound means we need to take out all the values. So first, let's look at this function, which even from here we can see that since f is a polynomial function, f is an exponential function, e to the x. So if we differentiate it 5 times, we still get e to the x. So this guy is just e to the zeta. All right, remember that exponential function is increasing in this interval. So the maximum so if I take the absolute value of this guy, it's going to be less or equal to e to the 1, which is e. It's increasing, so maximum is achieved at this at 1. And so I can now find the error now. The upper bound I'm looking for will be less or equal to each of these guys divided by 120, which is the first factorial, and the e, which we use to pound the f of. All right, so now If we are interested in actually computing the error band completely, we need to find the maximum of this polynomial, okay? But that's not what we want. According to the problem, we just need to find the upper bound at this point, okay? So when x is 0.25, we will get the interpolation error as the upper bound. Okay, so this would be 0.25. Less or equal to 0.25 times 0.25 squared minus 1, 0.25 squared minus 0.25 divided by 120 times b. Just substitute back and consider these as a difference of 2 squared. And if you do this, approximately this is 0.00095, which is like 9.95 times 10 to the power minus 4. Similarly, at x equals to 0.75, we have the interpolation error will be e of 0.75. Of course, if you want, it's f of 0.75 minus f hat of 0.75 is going to be less or equal to putting 0.75 instead for x. So you have 75 times 0.75 squared minus 1, 0.75 squared minus 0.75 over this should be 0.25. Okay, the difference of 2 square of this one gives x plus 1 over 2 times x plus minus 1 over 2 gives x squared minus 1 over 4. That's what I'm using in this side. And the other one is x plus 1 times x minus 1. That is the one that gives x squared. So x plus 1 times x minus 1 gives x squared minus 1. All right, so over 120 times e, this is approximately 0.00233, which is approximately 2.323 times 10 to the minus 3. I want you to take note of something here, okay? Take note. If you see what we get, that the first error is better than the second one. The interpolation error, okay, we tend to be smaller, okay, towards the center of the interpolation. So that is why when we have at 0 point. So the interval we have again is -1 to 1. So 0 is the center. Okay, so when we have x equal to 0.25, we have good error. When we have now something far away from the center, the error is reduced. So I will suggest that you try maybe x equals to 0.5 to see that you will get better. All right, I'm going to stop the presentation here, okay, because of the time. And I'm going to see you in my next video. I'm going to present something that is coming up on piecewise interpolating polynomial. Thank you very much. When you watch this video, if you have any comment, put it in the comment sections. And if you like this video, also, if you have questions, I will get back to the review and be able to answer your questions. I hope this helped all my students and every other person that takes advantage of this. See you in my next video. Thank you for watching.